our previous class, we solved some problems on differentiation, but we left one problem, and I said that I will be solving it in the next class because it's a bit time consuming, and this is that particular problem. Okay, so we're going to start with it. This is our question 1 for today. This came in 2011, and it is a multiple select question. For a function f of x, let di f of x upon dx raised to I at x equal to a denote its ith derivative with respect to x evaluated at x equal to a. Consider the matrix A given by aij n cross m of n greater than 1 rows and m greater than 1 columns, with aij given by di x raised to n upon dx raised to I at x equal to 1 upon or divided by dj y raised to m upon dy raised to j at y equal to 1. Let pi denote the maximum of aij's where j goes from 1 to m, and let qj denote the minimum of aij's as I goes from 1 to n. Let p denote minimum of pi's as I goes from 1 to n, and let q denote the maximum of qj's where j goes from 1 to m. Then p is greater than q, a11 less than a22 less than up to less than amm if n is greater than m. Anm equals an minus 1 comma m minus 1 is equal to up to an minus l plus 1 comma m minus l plus 1, where l is the minimum of n and m. In option D, it's a symmetric matrix if m is equal to n. Okay, so it's a quite a big problem. So let's start with the function given to us. Okay, the function that we are given is x raised to n or x raised to m. Okay, and this is our usual standard notation for ith derivative. We usually don't use I for that, we use n, but now they are using ith derivative, so that basically tells us ith order derivative. Okay, another thing that is unusual about this problem is we consider the order of a matrix as m by n, isn't it? We consider m by n like m rows and n columns, we say, but now here they are using n cross m, so you have to be careful in solving the problem. Okay, so it's not m into n, it's n into m. So n is the number of rows or the tally of rows, and m is the number of columns here. Okay, that is another change that you need to keep in mind. And then we are given a matrix. Okay, the matrix has n rows and m columns, and how do we calculate the entries of this matrix? The entries of this matrix are given by dividing one derivative by the other. Now the function that we are differentiating is x raised to n. Okay, so in the numerator we are differentiating that function as many times as the row number, and in the denominator we are differentiating the function as many times as the column number of that particular location, and we are substituting x and y, well, the value as 1. Okay, so what I'm going to do is I'm going to build a matrix, start building a matrix, and then we can have a better idea of what exactly is happening there. Okay, so suppose this is our matrix, and these are our rows r1, r2, r3, right? r1, r2, r3, then let me say rn minus 1, and then finally rn. And suppose these are our columns. Okay, suppose these are our columns c1, c2, c3, and now I need to write cm minus 1 and then finally cm. Okay, So in the first row and in the first column, I will be differentiating the function x raised to n for the rows, and for columns what I will be doing, let us say I call it g of y, okay, g of y, and let me call it y raised to m, right? That's what they have said, x raised to n and y raised to m, and now I need to differentiate them. Observe that in the whole of the first row we are differentiating f only once. Okay, so everywhere there I will have n and n, but in the denominator what will I have? We need to take the derivative of y raised to m, and so that is m into y raised to m minus 1. So I'll be just writing m because everywhere we want the derivatives value at x equal to 1 and at y equal to 1. So all we want is only the non-variable part or the constant part, like n into, well, n into 1 basically, then n into n minus 1 into 1 and so on. Okay, so if you get that pattern, then in the first row second column what would it be? It would be m into m minus 1. In the third column it would be third derivative. So first derivative is m into y raised to m minus 1, second derivative is m into m minus 1 into y raised to m minus 2. So third derivative will be m minus 1, m minus 2, and what will be the derivative here? It will be n upon, well, can I say that it is m minus 1, okay, not m minus 1 factorial, sorry. Here it would be m factorial, and here also it would be m factorial. Why? Because the actual derivative is m factorial into y, and when we substitute y as 1 it would become m factorial. Let me give you an example. Okay, let me give you an example. Suppose our function is x raised to 4. Okay, its first derivative will be 4x cubed, second derivative will be 12x squared, third derivative will be 24x, and fourth derivative will be 24. Now I want to draw your attention to the fact that this being a fourth degree polynomial x raised to 4, its fourth derivative is constant, but its third derivative is a linear function with the same coefficient, and because x and y both are 1, these two things will be common. I hope you understood that. Did you?
Yes, sir.
Okay, so let us now repeat the same process. You realize now that throughout our matrix, the denominators in every row, they will be the same essentially as these elements here, right? What will change then? The only thing that is going to change is our numerator. So let us do it to save our time. Okay, so this would be for R2, n into n minus 1, n into n minus 1, second derivative everywhere, n into n minus 1 and so on. Correct? Okay, maybe I should skip for R3 because we have now got the pattern. Okay. Okay. Now how about Rn minus 1? Do you realize that like it was the case with Cm minus 1, it was m factorial. Now for Rn minus 1 also everywhere we will have n factorial. Is it clear? Because that is the n minus 1th derivative of x raised to 1, right? And then in the denominator what will we have? Okay, so the same pattern will be there even for Rn. N factorial, n factorial, n factorial, n factorial, and n factorial here, and in the denominators here again it would be m into m minus 1, m into m minus 1, m into m minus 1 into m minus 2, m into m minus 1 into m minus 2. Here we will get m factorial, and here also we will get m factorial. Okay. factorial, m factorial, n factorial, and n factorial. Okay, so you need to build this matrix to have a better understanding of what exactly the problem is telling us. Clearly you now realize that in every row, okay, in every row the denominator is increasing, so the values are decreasing. Okay, and what do you see in the columns? In every column you see that denominator remains constant but numerator continues to increase. So in every column the largest element is at the bottom. Okay, in every column the largest element is at the bottom, but in every row the largest element is well at the left. Okay, so it's like that. Every row, okay, where is the largest element? Okay, in every row where is the largest element? Can anybody tell me? Largest element is in C1. Okay, and in every column, where is the largest element? Largest element is in Rn. Okay, alright, now let us see the options. Okay, what is Pi? Pi is the maximum of Aij where j goes from 1 to m. Now look, so Pi refers to some row, right? Pi refers to elements in a row, and we want maximum of the values. Okay, so what will be Pi? In every row, which element is the largest? N upon m is the largest here because everywhere else we are dividing by some other number. So the column of Pi is this. Have you understood this? Yes, sir. Yes, I can say this is the column of Pi's. Okay, so P1 is n upon m, P2 is n into n minus 1 upon m, and so on. Okay. Okay. And what is P? P is the minimum of all of them. Okay, so which element is the minimum of all of them? That is n upon m, right? That is n upon m because in the first column the least element is n upon m, correct? So P is n upon m. Okay, P is n upon m. Now let's go to Qj's. What are Qj's? Qj's are the minimum values of Aij where I goes from 1 to n. So now we are into columns. And which values do we want? We want the minimum values. Okay, we want the minimum value, and clearly row number is different. Okay, so we need to consider every column and we need to pick the least one. Okay, we need to pick the least one. Okay, now in every column largest element is in Rn, so what will be the smallest element? Obviously the smallest element will be in the first row. In every column the smallest element is in the first row. Do you agree to that? Because after that what is happening? Denominator is constant but numerator is being multiplied by something. So this would be the row of Qj. Okay, this is the row of Qj. And among them, what do we want? We want the maximum of that. Okay, we want the maximum. So for the maximum of the Qj values, we need to pick the one which has the smallest denominator, that is n upon m. So Q is also n upon m. P is n upon m, Q is n upon m. So is P greater than Q? No. P is equal to Q. So option A is not right. Okay, is it clear? Yes or no? Yes, sir. Yes, okay. Now let us come to option number B. Okay, let us come to option number B where they say A11 less than A22 less than AMM if n is greater than m. Okay, now pay attention. What is A11 here? Okay, A11 is n upon m. Okay, A11 is n upon m. A22 is n into n minus 1 upon m into m minus 1, and A33 n minus 1 n minus 2 upon m minus 1 m minus 2. Okay, and so on. Now what are they saying? They are saying that if n is greater than m, then the sequence that we have written is an increasing sequence. Now is it true? Is it true? If n is greater than m, n upon m will be greater than 1. That's okay. But n minus 1 upon m minus 1 will also be greater than 1. Okay, which means A22 is actually A11 into some number which is greater than 1. Right? What number is that? That number is this one. And same logic applies to n minus 2 upon m minus 2. So A33 is A22 into something which is greater than 1. Correct? And what is that something? That's this one. So essentially we are getting a sequence of numbers which are greater than all the preceding numbers. So is B right? Yes, B is right. And of course we cannot go after AMM because there are no wait, n is greater than m, right? Yeah, so there are no columns there. Okay, there are no enough columns left. So B is correct. B is correct. So have you understood that, or should I explain it again? Understood, right? Okay. Now let us come to option C. Okay, now let us come to option C, where they say ANN is equal to AN minus 1 m minus 1, and you have to continue this till AN minus L plus 1 comma m minus L plus 1, where L is the minimum of n and m. Okay, now I'll take C here. And put it here. Okay. Now everybody agrees that ANM would be what? N factorial upon m factorial. Right? This element. Nth row, mth column. Correct? Okay, so that is what was that? N factorial upon m factorial. Okay, now suppose I am interested in writing a n minus 1 comma m minus 1. I have seen that because x and y's values are 1, okay, this element has to be equal to it, isn't it? That's what we saw it here. 24x and 24, at x equal to 1 they will be equal because x is 1. So at least n minus 1 and m minus 1, they are concerned, we still have n factorial upon m factorial. Now what we have to do is we have to see how far back we can go with this logic. Okay, this is nth derivative, or okay, let's say nth, or let me put it in this way, d raised to n upon d raised to m. This is d raised to n minus 1 upon d raised to m minus 1. Okay, the order of the derivative, where d represents d by dx or d by dy. Okay, but now when it comes to a n minus 2 m minus 2, okay, when it comes to a n minus 2 comma m minus 2, what do you think do I need to write? Okay, well, it is actually np2 upon mp2. Now why am I suddenly bringing permutations here? Look here, when I differentiate nth order derivative, okay, when I differentiate a function n times, let's say x raised to n, what is the sequence of coefficients that I get? I get n first, n into n minus 1 second, n into n minus 1 into n minus 2 third, and what is the last derivative? Nth derivative is n factorial, n minus 1th derivative is also n factorial, and n minus 2th derivative is what? Okay, n minus 2th derivative is what? Can anybody tell me? it would be uh, n factorial upon n minus 1. Uh, Wait, no, sorry, not n factorial upon n minus 1. What would that be? Let's find out. Minus 2. Okay, wait. Need to spot the pattern. So this is first derivative. This is second derivative. This is third derivative. Okay, that is np2. Let's see what np2 is. N factorial upon n minus 2 factor. Yeah, that is n into. No, wait. Sorry, not np2, npn minus 2. My bad. npn minus 2. Sorry. My bad. Wait. First is n. Sorry. Let me go back to that x raised to 4 example for reference. 24. So this is 12, right? N factorial upon 2 factorial. Yes, correct. So this is n factorial upon 0 factorial, n factorial upon 1 factorial. Yeah, this should be n factorial upon 2 factorial. Okay, n factorial upon 2 factorial or n factorial upon 2 basically. Okay, and that is actually np n minus 2. This is np n minus 1 and this is np. Okay, and is this right? First order derivative, is it np 1? Yeah, that is np1. Okay, is this np2? N into n minus 1? Yes, that's correct. Right, n into n minus 1, and then we will basically get everything. So this is np3. So the point is when it comes to second differentiating, okay, differentiating till n minus 2 times, okay, differentiating till n minus 2 times, the numerator is what? Np n minus 2, and the denominator is mp m minus 2. Okay, now we have just now seen that this is n factorial upon 2, and this is what? This is m factorial upon 2. Which one? The denominator, mp m minus 2. So that is also n factorial upon m factorial. Now let's take a bit, let's extend it backwards, a n minus 3 comma m minus 3. Okay, now there, how many times are we differentiating the function? N minus 3 times. So effectively it would be n factorial upon 3 factorial. Okay, and that is actually np n minus 3. Okay, so you realize that every time we differentiate, we are actually dividing it by the corresponding factorial, right? So this would be np n minus 3 upon mp m minus 3, and that would be n factorial upon 6 upon m factorial upon 6, and that would again become n factorial upon m factorial. Okay, so it looks like this pattern will continue, but how long are we going to do that? Okay, how long are we going to do that? We can extend it until we either reach the first column or first row. Okay, until we reach either the first column or the first row, and remember we are starting from this. Okay, so which is more likely to be achieved first? Okay, look, every time we are shifting towards left and up. Okay, so every time we are climbing one row up and we are going one column to the left. So obviously if the number of columns is lesser, there will still be number of rows left above that, and similarly if number of rows is smaller, then there would still be some columns to the left of the top. a row there, or top, I think wherever we reach that. Okay, and therefore they have made that condition minimum of n comma m. Okay, minimum of n comma m. So option C is correct. Have you understood, or should I explain it again?
I understood parts of it.
Sorry.
Some parts of it. I mean, I understood option and everything, but when it came to options, I understood parts of this one.
Okay, so do you want option C to be explained again?
I just want us to, yes, what does option C mean?
Okay. Okay, let me explain option C once again. C, look here. Option C tells us that start with the last element of the matrix. Have you followed that? Start with the last element of the matrix.
Yes, sir.
And then you shift one row up and one column to the left. Is it clear?
Yes, sir.
Now, in a sense, it is telling us that you can continue this process of going along the line y equal to negative x, so to speak. But how far can we go? We definitely cannot come out of the matrix, which means if the matrix has more rows than columns, then we are likely to reach somewhere here. But there are still more rows left above the matrix, above wherever we have reached. Okay, and if the matrix has more columns, then we are likely to reach somewhere here, not definitely here. Is it clear? That means, let's say if our matrix has one column extra, then this journey would take us to this element C2, R1 C2, and let's say our matrix has more rows than columns, then let's say one row more, then our matrix would take us to here. Is that clear?
Yes, sir.
That's the only significance of that's the significance of this step that they have made, n minus l plus 1, m minus l plus 1, where l is the minimum of n and m. Is it clear? Yes or no?
Okay, so you're saying it should reach either 4 column. Yeah, okay.
Got it. Now let us go to, well, I should have told you right at the beginning of the differentiation that when you differentiate it first time and put x equal to 1, first derivative is n, second derivative is n minus 1, and third derivative is n into n minus 1 into n minus 2. Have you understood that?
Yes, sir.
And nth derivative is n factorial, but n minus 1th derivative is also n factorial. It's actually n factorial into 1, so that doesn't count. And then we have got this n minus 2th derivative. And if you see the pattern here, first derivative is n, second derivative is n into n minus 1. That is clearly np2, because npr is n factorial upon n minus r factorial. And how much is that? That is nothing but n into n minus 1. So if we are finding the second order derivative, then it is np2. If you are finding the third order derivative, then it is np3. Right? So if we are finding the nth order derivative, it would be npn, n minus 1th order derivative, npn minus 1, n minus 2th order derivative, npn minus 2, and goes on. That just goes on. Is it clear?
Yes, sir.
Yes, so that's exactly what I did here. I said if I want to find a n minus 2, m minus 2 for the case here, it would just be npn minus 2 upon npm minus 2, and that would be just n factorial by 2 upon m factorial by 2. Got it? Which will lead to cancellation of 2 2. Okay, and yeah, and for npn minus, yeah, exactly. So that will get cancelled. Clear?
Yes, sir.
Okay. Now let us come to option D. Okay, let us come to option D. They are saying A is a symmetric matrix if M is equal to N. Okay. They're saying A is a symmetric matrix if M is equal to N. Now, look here. This can be proved very easily that it is not true. Look, if A is a symmetric matrix, or rather if M is equal to N, then N and M would be same, so this one will become 1, N upon M. But what about R1C2 and R2C1? Here we will have N into N minus 1 upon N, so that would be N minus 1, and here it would be N upon N into N minus 1, so it would be 1 upon M minus 1. Got it? Let me do it here.
So one will be greater than the other.
Yeah, so for N equal to M, this would be true. That this is 1. But what will come in the place of N upon M into M minus 1? There we will have N upon N into N minus 1, and here what will we have? N into N minus 1 upon N. Now how can they be same? Okay, they cannot be same because of 1 upon N minus 1, and here it is N minus 1, so they can never be same, right? For no natural number they will ever be same. So is option D right? No, option D is not right. Got it or no?
What is that?
Yeah. I just wonder who would have solved this particular problem. Maybe if somebody is fast enough in guessing the patterns, then he or she could have solved a problem in some time. Okay, got it? That was the first question, and that's the reason I didn't take it yesterday, because I knew that problem is lengthy. It was not difficult, but just to spot the pattern, it takes us so much time. Took us so much time, right? Yeah.
You have to know which function to apply, all the right steps.
Sorry?
You have to know the right steps, like
Yeah, that permutation part, if you are able to guess it correctly, I think that is going to save your time a lot. Okay, I should have told you right at the beginning, because had I told you at the beginning, we would have taken slightly less time in guessing the pattern. Anyways, okay, so that was the pending question. Now we can resume solving the other. Okay. All right. Let us now start with this one. This is our question 2 for the day. This came in 2020. Okay, I just want to tell you one thing. Do you know that I've already uploaded NEST 2020 math solutions on YouTube?
Don't know.
Right.
All the videos I have watched are like this.
I mean, I can still solve them for you if you want. But because the solutions are already available to you, is it okay if I go to questions which are not from those years, 16, 17, 19, 20? Okay. So, okay, in that case, let us go to question number 2, this one. Okay. The function f from R to R is defined as follows. F of x is equal to e to the power negative 1 upon mod x not equal to 0, and is equal to 0 when x is equal to 0. Then f is differentiable and its derivative is continuous. F is nowhere continuous on R. F is continuous but not differentiable. F is differentiable and its derivative is not continuous. This came in 2021 second shift. Okay, 2021 second shift. Alright, let us go to the function. Function is e to the power negative 1 upon mod x when x is not equal to 0, and it is 0 when x is equal to 0. Okay. Now as usual we will do it the mod way, so it will be e raised to 1 upon x for x positive, and it would be e raised to 1 upon x for x negative. Okay, now let us go to option B first. B is wrong because they are saying it is nowhere continuous, but without investigating for the continuity of this function at 0, we know that it is continuous at least okay, let me put it this way: it is continuous at least when x is not equal to 0. You take any other point, the function will be well defined, right? So B is wrong. Now let us see whether the function is continuous at x equal to 0. Okay, let us check if f is continuous at x equal to 0. We can argue like this. Look, let us find RHL first. Okay, now if x is positive, okay, if x is positive as x tends to 0, what happens to 1 upon x? 1 upon x tends to infinity. What will happen to negative 1 upon x? Negative 1 upon x will tend to negative infinity, and therefore what will happen to e raised to negative 1 upon x? It will tend to 0. Okay, have you understood this? If x is large, okay, sorry, if x is positive, 1 upon x will be also positive, and if x approaches 0, 1 upon x will tend to infinity, negative 1 upon x will tend to negative infinity, and e raised to negative 1 upon x will tend to 0. Okay, so RHL is 0. So at least it is continuous from right. Now is it continuous from left also? Let us argue like this: if x is negative and x approaches 0, what will happen to 1 upon x? 1 upon x will clearly approach negative infinity, and therefore e raised to 1 upon x will approach 0. Therefore left hand limit will also be 0, so therefore it is continuous everywhere. Okay, it is continuous everywhere. I don't see any problem regarding the differentiability of this function at non-zero values. You know how to differentiate it, isn't it? Okay, so let us investigate for its differentiability at 0. Okay, let us investigate for its differentiability at x equal to 0. Okay, at x equal to 0. Suppose we are finding the right hand derivative. Okay, suppose we are finding the right hand derivative of this function at x equal to 0. Which definition are we going to use for right hand derivative? E raised to negative 1 upon x is the definition. E raised to negative 1 upon x, sorry. Let's take the derivative. Okay, what would it be? E raised to negative 1 upon x into 1 upon x squared. Okay, f dash of x will be e raised to negative 1 upon x into 1 upon x squared. Okay, what can we do now? We would like to see the limit of this function, right? Okay, wait. Let's use first principle. Limit as h tends to 0, f of h minus f of 0 upon h. F of 0 is 0 because we have looked for it. Limit as h tends to 0 plus, what will be f of h then? E raised to negative 1 upon h upon h. Okay. Uh, I can apply L'Hospital here because it is indeed giving me 0 by 0. That's what we did here. E raised to negative 1 upon h. Okay. For this part, I can use L'Hospital there. So numerator will be what? E raised to negative 1 upon h into 1 upon h squared, and okay, it is not taking us anywhere. Okay, what can we do now? To check the differentiability at 0. Okay, suppose I go for left hand derivative also, then there the function's definition is what? E raised to 1 upon x. So what will be the derivative? E raised to 1 upon x into negative 1 upon x square. Okay, continuity is clear. Differentiable. Problem is with the limit of e raised to negative 1 upon h. Acha, I have one hint. Okay, instead of applying the L'Hospital's rule, which is unnecessarily increasing the complications, I can make some assumption here. Okay, so I can say let 1 upon h be t. Okay, I can say let 1 upon h be t. Therefore, as h tends to 0 plus, t will tend to infinity. I definitely know that. So I get limit as t tends to infinity, e raised to negative t into t. I hope you understood that. Right? Okay, great. Now I can apply L'Hospital here. Okay, now I can apply L'Hospital here. It will be 1 upon e raised to t, and that will be 0. Yes, so right hand derivative is 0. Okay, right hand derivative is 0. And okay, can we find left hand derivative in a similar way? Okay, let us see. Let us see if we can find the left hand derivative. F of x is e raised to 1 upon x. Okay, so limit as h tends to 0 minus f of 0 plus h, so it's e raised to 1 upon h minus f of h upon h. Okay, again I can make a change. I can say As h tends to 0 minus, minus h will tend to 0 plus. So let me say, let minus h be u. Okay, so limit as u tends to 0 from right, this will be e raised to negative 1 upon u upon negative u. But see, our one of our limits here is exactly the same thing, e raised to negative 1 upon h, and that limit was 0. So this will also be 0. So both LHD and RHD are 0. Okay, so differentiable at 0. Whew, okay, so at least we have proved that it is differentiable at 0, and also of course it is differentiable everywhere, so not differentiable is also not false, not true. Now we have to see whether its derivative is continuous. Now how to check whether its derivative is continuous? Go back to the derivative, left hand right hand derivatives, and evaluate their limits. Okay, that is limit as x tends to 0 plus this one, see, look here, for this also I can use the substitution 1 upon x tending to infinity. Okay, so it will be t squared upon e raised to t, this will be 0, right, by the same logic as t upon e raised to t was 0. And similarly x tends to 0 from left, there we have got, I think, 1 upon x into negative 1 upon x squared, and that would be how much? Again we can bring in those changes. Okay, again we can bring in those changes, and okay, let me write it. Suppose I say that negative x is v, so v tends to 0 plus e raised to negative 1 upon v into negative 1 upon v square, and that's basically the same as this except the negative sign, so this will also be 0, so the derivative is continuous. Okay, the derivative is continuous. Is it clear, or shall I explain it again? Clear, right? Okay, fine. Can you solve this question at home or right now? I'll give you some time. Yes, if you want you can try it now. I'll give you 5 minutes.
V.
B. Okay, minimum of x cube and x squared, so definitely it is like this because x squared is this, and then after this it would be x squared, I suppose, at 1, and because the x cube is less than x squared for values of x which are less than 1, would be something like this. Yes, it is differentiable everywhere except at 1, because the left hand derivative will be 3x squared at 1, so 3, right hand derivative will be 2x, so 2, correct, option B. Rajat, was it you or Danish? Okay, Danish. Take it, good. Fine then, I'll stop here for today. We couldn't solve much because the questions were of that kind. Tomorrow we will continue with the remaining sums.